So while I'm checking homework, we're going to do some practice problems. Not all of these, we were working on these this morning. But let's start with number 16 because I don't think we've seen one quite like that. That's particularly challenging. So I'm going to pause the video while I'm checking homework and then we'll come back and see how to do that. You ready to take a look at that one? How do we do? Okay, so the idea behind it is we have that our pH is 7.5, but that's not a count exactly of how many of these hydrogen ions we have. So our formula is this, the pH is negative log of, and we use this kind of weird symbol with the brackets and the capital H plus. This is not exactly, but kind of a count of how many of these hydrogen ions we have. So what we want to do is get to that number so that we can increase it by 60%. And then once we have a new count of how many of those hydrogen ions we have, then go back and see what the pH of that is. So first, to get to the number of hydrogen ions, this H plus, we're going to set the pH equal to that 7.5. We'll multiply the negative to the other side, and then we'll raise it to the power of 10. So we're going to get that H plus to be 10 to the negative 7.5 power. And you can throw that on your calculator if you like, or you can just leave it like that, either way. Now that's, in a sense, then how many of these hydrogen ions we have. That's going to increase by 60%. So then how many are we going to have? How many of those hydrogen ions will we have after it's increased by 60%? How do we figure it out?
Multiply that by 1.6?
Yeah, multiply by 1.6, right? Because multiplying by 1 would be the same amount. We're increasing, so we're going to multiply this number by 1.6. So that's how many hydrogen ions we're going to have in 2050. And now we want to find the pH of that. So this is our new H plus in 2050. And then to find its pH, we're now going to take the negative. So the new pH is going to be the negative log of this. And when you do that, it's like 7.296. It's about 7.3. So you can see that because this scale is logarithmic, even though we increased it by 60%, the change from 7.5 to 7.3 was pretty small. So a small change in pH can represent a big change in the number of hydrogen ions. All right, you want to pick any one of those look particularly challenging that you think would be good practice?
12.
Number 12. So here we have find the half. This is one of those tricky ones. Oh, no, this isn't the 2 and 1. Okay, so let's try number 12. And should we come to the board and do this? Find the half-life of a substance that decays at 9.3% per day. So half can come willingly. I'm going to pause this for a moment while we work. Looks like we're reaching agreement here. So since we're decaying by 9.3% per day, that's going to be 1 minus the 0.093 to the t, and that's going to give us, we want to know how long is it going to take to get half of that. And so it doesn't really matter how much we start with. So we're going to get our 1/2. And that's going to be what, 0.9, is that 0.07? Is that what that looks like to the t? So we're going to take the log of both sides, doesn't matter what base. And if we want, we can say that's log 1 minus log 2. I never pass up an opportunity to try to keep those logarithm skills sharp. Log any base of 1 is 0, so that's going to be a negative log 2 over the log of 0.907. And I think we're finding that to be 7.101 days. Okay. Good to go. Okay, if you want more practice, come on in after school or before school. Remember, we're testing Friday at 9:30 in the cafeteria. You can set your alarm back. We can sleep in a little bit unless you have AP Physics, in which case keep your alarm set early because they've got the early time slot there. Questions on any of the homeworks that you would like to see done? Yes, Ben?
Homework 39, question 25 and 27.
25.
I don't know what they are. So I think they're on page 240 something.
Page 240 something?
47.
47. Okay, let me see if I can find it. And 25 and 27. So, oh, these are tough, yeah. So this is referring to functions obtained by applying a transformation. And so we know for our function p of n, we're told that its domain is going to be -2 less than n less than or equal to 8. And the range goes from -6 less than or equal to p of n less than 12. So there's our domain and range of p of n. And in 25, we want to find the domain and range of r of n. Oh, wait. No, we're told that the domain and range of a new function, r of n, is going to be -3 to 8. -3 less than n less than or equal to 8. And its range is going to be -60 to, I think, is that 30? 60, right one, less than r of n, less than or equal to 30. And then we want to figure out r of n is some transformation of p of n. So we're trying to get r of n is equal to, what do we do to the p of n? Are we going to do some kind of transformation inside? Or are we going to do some kind of transformation outside? So let's see, let's look at the inside stuff first. So we compare the domain of p of n to the domain of r of n. Did I get that right? That doesn't look like it's what I want. See, domain went from -3 to 8. Well, this was a -3. Otherwise, that was going to be really hard. So in this case, they stay the same, which means we're not doing anything with the inside part there. So there's no translation horizontally. There's no stretch or shrink horizontally. It's just the same. So now we can look at the range part. So what are we doing to this on the outside? Are we stretching it, shrinking it, reflecting it, translating it, or some combination of those? So when you look at what's happening from the range here to the range here, and let's see, make sure we got that right. So the range -60 to 30, and the original was -6 to 12. Okay, because at first glance it looks. What's that?
Times -5.
Say it again.
Because it flips and then both of the numbers are times 5.
Nice. And you can kind of see that. I think you see what Nora's saying? Oh, that's really quick and insightful there. So this kind of gives a clue too, because you see that the or equal to is on the lower part, but it's switched here. So for those to switch means there must have been some kind of negative. You multiplied or divided by a negative. So if we multiply by a negative, then these are going to switch. So you're trying to say, what are we doing to the -6 to match it with the 30? And we're trying to think of the same thing it's gonna match the 12 to the negative 60. That makes sense? So the negative is certainly a part of it. So we're gonna multiply by a negative. And I think Nora sees it too. Do you see that if you multiply the negative 6 by negative 5, it's going to become positive 30. And also the negative 5 times 12 will make it a negative 60. And so that's going to become our transformation. These are tough because it's like a big puzzle and you've got little pieces, but you have to almost kind of make them fit all at the same time because it's got to make both of them work. So let's try 27. And if we have some time today, I'm hoping I've got some more examples of this we can try to. It just takes some practice, I think, in trying to sort it out. So we still have the same P of n with its same domain and range. So I'm just going to get this one out of the way and take that out of the way. And 27 is now saying the domain of T of n is negative 10 to 1. So its domain is going to be what I said, negative 10 to 1, and I don't remember, let me see which ones. One of those is an or equal to, one is not. So it's on the or equal to goes here. And the range for our T of n is going to be from negative 1.5 to 3, negative 1.5 to 3. And so first on the domain, let's look at that first. And I would check where the or equal to sign goes. Does it stay in the same relative order or not? And you can see these both have the strict inequality and then the or equal to. And that's a clue that we're not going to multiply through by a negative. So if those are in different places, that means we must have multiplied by some kind of negative. So we're not doing that. So now we're trying to ask ourselves, what are we doing to the negative 3 to get to negative 10? And it has to be the same thing to go from the 8 to the 1. And I think, yeah. Can you see it? So we're looking at these from negative 3 to negative 10. What do you do to the negative 3 to get to negative 10? And can you do that same thing to the 8 to get to 7? Say it again. Instead of adding 7, I think subtracting 7.
Yeah.
Is that okay? Okay. So that means our R of n is going to be, and now this is going to be inside because it's affecting the domain. And so what we want to do is now we got to think about this. We want this to be, so I think it's going to actually be an n plus 7, right? It's because we want to move everything to the left 7 so that when we use this as our domain with this, it's going to take us back to the same domain there. So if we plug a negative 10 into our T of n, or I guess this is T of n now, then when we plug in negative 10 plus 7, that's negative 3, which is going to be defined in the P of n. So that's the way we want to do that one, okay? Now we can look at the range part. So what are we doing here to get to here? And again, I would look at the inequalities first. So since they are not switching position, we're not multiplying by a negative. So now it's either going to be just adding or subtracting something, multiplying by a positive, or a combination of a multiplication and adding and subtracting. So what do you think? I know Nora's on this. He is good at this. Okay, so either dividing by 4, which is like multiplying by 1/4. Might be easier to see here.
Wait,
12.
aren't you trying to go from the new to the old, not the old to the new? So it'd be multiplying by 4.
It works, that's the way it works with the domain, but the range works the other way. I know it's weird. So you actually do them differently for domain than range. So in the domain, you're going to go from here to get to here. But then once you plug these numbers in, that's going to give you this with the P of this. and then we're gonna change it to get to there. Does that make sense, what we're saying there? So you go a different direction. So we're trying to go from here to there with domain, but from here to there with range. And so we can divide this by 4, multiply by 1/4, and that turns out to do the same thing we want over there. So that is going to be a 1/4. Those are tough, no question. Anything else? Okay, so let me pick up where we left off last time and build on that. If we can, I have some more examples of this kind of stuff we'll try to fit in as well. But there's some other things like this we're going to do that are pretty tough also, and I think it will help us think in a similar fashion about how to try to do these. So right at the end, we were talking about if we had something in factored form. So let me refresh your memory on this, and let me start the camera rolling. I think it's still rolling. Okay. So we talked about the factored form versus the unfactored form, and we'll do some actual examples of graphing this. So I'm going to put them in different colors there. A times F of, and then B, and then we'll say times X minus C, and then a plus, and we'll say D. So in this factored form, we'll see these numbers in different places. And what happens is that this number that you see outside the function, that's going to be the vertical stretch or shrink. So if this number is bigger than 1, it's going to stretch. If that number is smaller than 1, it's going to shrink. So that is a vertical stretch or shrink. And the part in here, the thing that is multiplying the x, right, because this would ultimately multiply the x, that's going to be the horizontal stretch or shrink. And this is the one that is, I think, the most difficult, but I could be wrong there. So this is the one that we've talked about is counterintuitive. So a bigger number for B, something that's bigger than 1, is going to actually shrink it horizontally. And a number that is less than 1 is going to stretch it. So that we're kind of thinking of, or at least I do, I think of it as being like a time thing. So a bigger number is going to speed things up and make it go faster. A smaller number is going to slow it down and stretch it out horizontally. The C, we have seen quite a bit of this already. It's a translation in the X, or some people call it a shift. And remember, when you see that, it is the opposite of what you see. So if you see an x minus 5 inside the function, that means you're going to move it a positive 5, a right 5. If you see an x plus 2, that's going to move it left 2. So it kind of goes in the reverse. Kind of like we've seen, these are kind of both doing that. They do maybe the opposite direction of what you might think. Okay. And then the D is going to be the vertical translation, or some people call it a vertical shift. And so that is going to move everything in the Y direction, and there it's going to be the same value of what you see. And so if you see a positive 4, that's going to move everything up 4. If you see a minus 2, that's going to move everything down 2. Now we will see this at times where it is not factored. So the, I guess I'll call it the unfactored form. And so be careful. When you see something in the unfactored form, it's easy to be misled on what that translation is going to be horizontally. So we might see something like A times F of, and I hesitate to even call this C, so, but I'm going to leave it there as now. So here, when you see that the B has not been factored out of everything inside the function there, when it has not been factored, this is not the translation horizontally, because it's being distorted by the B that has distributed to that. So when you see that, what we are going to do is first factor that B out, and then that's going to become something different. You don't have to memorize what it is, but we're going to have to factor that B out, and then we'll be able to tell what the translation is horizontally. All right, so let's tackle one of these. I'm going to give you one with all the stuff in there. First, I'm going to give it to you in factored form. I'm going to give you a function that is not linear, so that will, I think, make us see more clearly what the different effects of each of these are. And then we'll do another one that is not factored, and we'll see how we'll deal with that. Okay, so let's try y is equal to, let's go -2 and square root of 1/2 x minus 1 plus 2. So our f of x here is that square root of x function. So that's our parent function. And you can see we're going to do all these different things to it. Now first I'm going to put in white the parent function that we're going to kind of use as our comparison, and then we'll see how that's going to change. So our parent function, remember, contains these two notable points, 0, 0, and 1, 1. And so those are where we're kind of playing off of that, okay? All right, so we know that, let's just talk about what is going to be first, I guess, before we start plotting points here. So what is the negative going to do? It's going to flip it, right? So we're going to get something that's flipped over the x-axis. It's going to come down to the right this way. What is this 2 going to do? That's a vertical stretch. So instead of going up 1 and over 1, we're going to go up 2 and over 1. And what does this 1/2 do? That's the horizontal stretch, right? So instead of going... No, see, this is the one that's counterintuitive. So we see a smaller number, but it's actually going to stretch it horizontally. So instead of going over 1 to get to this point, we're going to go over 2 once we get there.
So would it go back to just 2, 2? It's just...
Well, we will go up 2 because of this,
yeah,
and we're going to go over 2 because of that.
Okay.
So it's
And,
kind of, it's kind of like.
but that's not the same as going up 1 over 1. Okay, so that's the part, because this is not linear. If it was a line, then going up 1 over 1 would be the same as going up 2 over 2.
So does it kind of like enlarge it as a whole?
Yeah, so the vertical part, in a sense, well, the vertical part's going to stretch it this way, but the horizontal part is going to stretch it this way. So they're kind of working against each other a little bit. Okay, because a vertical stretch would look a lot like a horizontal shrink, but a vertical stretch and a horizontal stretch kind of are competing against each other. But they won't exactly cancel each other out because one's happening outside the square root and the other one's happening inside the square root. So the one outside is going to have a little bit more impact than the one inside because it's being muted by the square root. Does that kind of make sense? And then we're going to move it, what's this, right 1 and up 2. Okay. Now, what we can do is the point 0, 0 is going to be unchanged by the vertical and horizontal stretches and shrinks because it's got 0 in it. But it will be affected by the translation. So that starting point 0, 0 is going to just move to 1, 2. Does that make sense? So I'm going to go to the point 1, 2. 1, 2. And that's going to be where the 0, 0 gets moved. That's kind of our starting point if we want to think of this graph. Is that okay? Now, the 1, 1, the translation part is going to be taken into account by, we're going to play off of this point that's already been moved. And so then we're going to use now both the reflection, the vertical stretch, and the horizontal stretch. we're gonna do as going from this point. So we said the negative part means it's gonna be going down instead of up. And the vertical stretch means we're gonna go down 2, and the horizontal stretch means we're gonna go right 2 as well. So we can get that second point, which is gonna then get us in the right shape by from the translated 0, 0, we're gonna go down 2 for the reflection and the vertical stretch, and right 2. So going down 2 and right 2 is going to put us at this point right here. You with me then? And that's going to be the point 3, 0. And then we can connect these with, now it's not linear, so it's going to be this, trying to, I almost missed that point there. Let's make it a little bigger. So it's going to be that bottom half of a sideways parabola. Make sense? Okay, so that I'm hearing you're ready to do one of these on your own. Now, I'm going to give you one that is not factored. So what you have to do first is inside the function, factor it before you start deciding what the translation and all that stuff is. Okay, so let's do y is equal to 1/2 big square root, and we're going to have a negative 2x plus 4, and then minus 1. Okay, are we ready to come to the board to do this, or are we not feeling confident? I think we're ready for it. I'm going to pause the video, give you a chance to work on this at home as well, and then we'll see if we can come to agreement. So our point 0, 0, that's where our parent function, we're going to start at 0, 0, we're going to contain the point 1, 1. It's looking like that. Now, the point 0, 0 is unaffected by our stretches and shrinks. I guess I should factor in here. So inside here, we're factoring out that negative 2, and so our function is going to look like this in factored form. So the point 0, 0 is unaffected by the vertical shrink and the horizontal shrink and reflection in the y, and so we're going to just move it to 2, negative 1. So it's going to be right here at 2, negative 1. So that's where the point 0, 0 on our graph has moved. Now we're going to, since we've reflected in the y, this is going to be going up and to the left if we want to think of it as starting from 0, 0. Because of the vertical shrink, instead of going up 1, we're going to go up 1/2. Because of the horizontal shrink, instead of going over 1, we're going to go over 1/2. And because this is not linear, going up 1/2 and over 1/2 is not the same as going up 1 and over 1. So we can't just try to dodge the fraction part of this, unfortunately. So going up 1/2 and over 1/2, I think is going to make that x coordinate be 3/2 or 1.5 either way, and the y coordinate be negative 1/2. And then we're going to try to draw that top half of a parabola that's opening to the left. Okay? Okay, so let's change the kind of problem we're going to do a little bit here, still using this idea of transformations. So working on our way to build a little confidence before I crush it. We're going to find if the domain and range of our function f of x is, we'll say, negative 2 less than x less than or equal to 6 for the domain, and negative 4 less than or equal to f of x, which is strictly less than 10, can, if the domain and range of f of x is given there, and can we find the domain and range of, first of all, like I said, we'll be gentle here. G of x is going to be 2 times f of negative x. 2 times f of negative x. All right, so what's the new domain for G going to be? Ben, you want to give it a shot?
Negative 6 is less than or equal to x is less than 2.
Sounds good. We agreement? Okay, and how about the range? Claire, you want to give that one a shot?
I don't know, I didn't get to the range yet, I'm a little bit confused.
Okay, so fair enough. So I think Nora said it really well. With a domain, we want to pick this domain so that when we plug in a negative x there, it's going to take us back to here. With the range, we go the other way around. We're going to start with this range, and then we're going to multiply it by this and see what that new range becomes. So if we look at the range that we have, and we're going to multiply it by the 2.
So it'd be -8, and then,
Multiply by a positive 2, so the inequalities are going to stay the same.
20.
Well, we skipped over some important stuff there.
Oh, less than or equal to,
And we can say g of x or y, I'm not really worried about that. And then 20 is correct. Okay? All right. So let's say now that we're going to say h of x is going to be negative 3 times f of x minus 2. So that's the transformed f of x. So with this as our function, what's the new domain and range going to be? Can you come up with that? I'm going to pause the video while we work on it. All right, Emma, you want to give it a shot for the domain? What do you think?
-4 is less than x is less than or equal to 4.
So negative 4 less than x less than or equal to 4. I don't think that's right, though. Because if we plug this negative 4 in for that x, it would give us a negative 6, which is not in our domain. How did you want to explain it, Ashlyn?
I was just going to say I think you need to add 2 rather than subtract.
Yeah. So you could think of, with this one, plugging this in where that is, and then getting the x by itself. So you're actually going to add 2 to both sides there. It goes the other way with range. So the way you're thinking would have worked is going to work for range, but you're going in the reverse order for domain. So it should be, how should it be? You see?
So instead of it being -2, it'd be +2.
So right, or another way, I mean, we can think of it a couple of ways. Visually, this is going to be translated right to. And so this is where our left and right are. When we move that right to,
So it'd be 0 is less than x is less than or equal to 8.
correct. Now it goes the other way with range. So Ashlyn, how about the range? What would you get for that one?
shot in the dark. -30 is, less than, whatever, h of x,
H of X, yeah.
which is less than or equal to 12.
Good shots. Mhm. So this one is like what you were thinking, Emma, you're just gonna multiply that range by the -3. And that's gonna take us to there. And if you had just, if you'd written in the other order, so if you had written 12 is greater than or equal to h of x is greater than -3, that's equivalent, so that would have still been correct. I think this reads a little nicer because you're going from small to big. Okay, well, let's change. We got some harder ones to do, and we're running short on time here. So let's see if we have, first, the graph of f of x of y equals f of x contains the point 2, -3. What point must be on the graph of y equals, let's see, -3 f of 2 times x minus 4 plus 5. So that point on f of x, what point must be on this? This is tough. It's kind of the same sort of thinking that happens with our domain and range questions. So what are you going to plug in for x here that after you do all of this stuff is going to make you evaluate f of 2? Right? The inside part is the harder one. Then once you evaluate f of 2, this is all going to be -3. And then you're going to do that stuff to it to get the y coordinate. What was your x coordinate, Ron?
3?
I don't think so.
I think that's wrong.
I would agree with the second part. Not wrong. Not correct. Isabel, what did you get?
5?
Nice. We're trying to get 5 for the x value. How? So one way of thinking of it is, remember, the only thing we know how to evaluate is f of 2. So whatever we choose for x has to result in, after all this arithmetic, it has to leave us with evaluating f of 2. Which means we could, you could do this very algebraically and say whatever this is has to end up equaling 2. Now, solve that. 2.
Oh, because for some reason they added before dividing.
Yeah, so I think trying to think it visually isn't maybe the best way to try to approach it. Is this how you did it, Isabella? Yeah, this is what I've tried a few different ways. I think this is the one that's the most reliable for me. So now let's just see what we're saying. When we choose x to be 5, we plug it in here. Now, order of operations, we'd go 5 minus 4 is 1, times 2 is 2. Oh, that's good. We evaluate f of 2. That's the only thing we could do, because that's the only place where we know the y value is at 2. Now, once we do that, this has become a -3. Right? Now, we just do the arithmetic there to see what the new y coordinate is going to be. So that's going to be, waiting for it, 14. So the point is going to be 514. I was running the video. Okay.
Wait, but wouldn't you do like what you did for x and leave f of x as its own thing?
See, and that's, see, they work differently. Remember, you had a handle on this when we were doing domain and range. It's the same thing here. So you kind of approach them differently. You want this to be that, but then once you plug in whatever X value you choose, now you get this Y value, and then you see what happens to that after the fact.
Oh,
So it's kind of, yeah, you approach them differently.
okay.
Okay, well, I was going to try to give you a domain and range. I don't know that we're going to have enough time. We'll keep talking about these. I know these are really hard. Okay, but hopefully this will give you a fighting chance at your homework for tonight.